welcome to the third season of our course on large language model in practice. And I think let's start our course now. So welcome. And today's topic is one I'm really excited about, the sustainable AI in action. So to measuring and building the green and the efficient large language model. And I'm Yiling, and now together we will explore how we can build the large language model more responsibly with the planet in mind. Yeah. So this session has two parts, a lecture and a lab. First, I will introduce the concept of the sustainable AI, the energy impact of the large language models, and how we can measure and reduce that. Then we will move into a hands-on lab where you can apply what you have learned today into the lab. So let's start by looking at how computing power in AI has evolved. In this chart, you can see this shows something very important. The amount of computing power used to train AI system has grown quickly, especially in recent years. If you look closely, the y-axis shows the days of computational at one petaflop per session. That is a huge amount of processing, and this is on a log scale, which means every step up is a 10 times increase. So training today's powerful AI model requires massive energy and hardware resources, and that growth is accelerating. Yeah. So now, before we go any further, it is important to clarify what we actually mean by sustainable AI and how it's different from other popular terms, the AI for sustainability. So you might hear these two used in similar contexts, but they focus on very different goals. The sustainable AI means making AI itself more environmentally responsible by reducing the energy and the carbon footprint of the AI model, especially the large one like the large language model. And on the other hand, AI for sustainability means using AI as a tool to solve the sustainability problem in different industry. So in this lecture today, we will focus on the sustainable AI to reducing the environmental impact of the AI model. So let's define the sustainable AI more precisely. The sustainable AI is sometimes also called green AI or eco-friendly AI. These are popular terms that all point to the same idea. It's referred to the practice of developing and deploying AI technology in a way that reduces the carbon and the ecological footprint, not just during the training or use, but throughout the entire life cycle. So as you can see, these slides show why sustainability in AI really matters. It's compare the carbon footprint of some familiar things like taking a flight, living for a year, and driving a car. So at the bottom, you can see the impact of training just one NLP model, the large transformer model with 230 million parameters. The carbon emission from that training process are more than 626,000 pounds of the carbon emission. So that is more than 5 cars, including all the fuel, they burn over the entire lifetimes. So if we don't think about this now, the carbon cost of AI will continue to grow and fast. And this is the complexity, shows the complexity of the real world machine learning pipeline for collecting and clean data to the model development to deployment and monitoring. So every stage requires specific tools, the industries and the expert. So it is highly technical and resource heavy process. But there is also a big issue when only a small number of companies or industries have the money, the data, and the computing power to build large models like this. It creates a serious imbalance. So the AI development become more centralized. So it's controlled by a few big player who can afford to run massive model, publish more, and scale faster. So that's create a circle. The better the model, the more user will be attracted, and the more data they collect, and the more powerful they become. So this makes it harder for the smaller companies, also the researchers from the less funded labs or teams in the underrepresented region to keep up. So the barrier to entire keep rising, not just in cost, but like in the technical operation, access to the GPUs, and even the chance to public as the top conference. So this is why we need the sustainable AI, because the way we build AI today has some serious problem. First is a lot of data used to train AI is collected in a way that that's not fair. So people don't always know the data being used. This is called the exploitative data practice, and it's not sustainable from the ethically or the socially. And the second, AI is mostly controlled by a few big companies. They have the money, they have the data, and the computing power is lead to centralize of the power. So smaller teams or researchers can't compete, and that make the AI world less fair and less diverse. And third, the large AI model use a huge amount of the energy. That means the carbon dioxide emission and more harm to the environment. So the sustainable AI try to fix them, like by using data responsibility and by supporting open access and fairness, and by building AI that's using the less energy. So now let's focusing on the large language model. To understand the full carbon footprint of the large language model, we need to look at two main source of the emission. The first is the embodied emission and the operational emission. So the embodied emission is come from making the hardware, like the GPU, the servers, and the cooling system. This emission happened before the model is even trained. Many reports actually skip this part, but studies show this can make up about 1/4 to 1/3 of the model total carbon footprint. So that's also important. And one is the operational emissions. That's happened when we use the model during the training and also during the inference. Training large language model, training the models takes a lot of energy, often using hundreds of powerful GPUs for weeks or even months. So this energy use create carbon emission, especially if the electricity comes from the fossil fuels. So there are also hidden emission from things like storage, the networking, and keep the data center cooling. So this often overlooked, but still important. And we can see here shows a comparison of the energy use and carbon emission from training different large language model. It's only always easy to compare them directly because not all the information is public. So numbers here had to be estimated, especially for the things like idle energy use. So still we can see some interesting trends here, like the GPT-3 and the G4 have very high emissions, over 580 tons of the carbon emission, mostly because they were trained on energy intensive hardware and likely on the energy grid with more fossil fuel. And like the OPT use less energy and this carbon impact is lower, about 17 tons. And the interesting is the bloom, even though it's used more electricity than the OPT, but the total emissions were much lower, only like 25 tons of the carbon emission. That is because blown was trained on in a French supercomputer that's powered mostly by the cleaner energy. And so far, we talked a lot about the energy needed to train the large models. But how about the inferences? The inference means using the model every time someone asks the question or get a response. It's use less energy per query, but training only happened once. Yeah, but the inference happened millions of times. So in this table, we can see the different vision of the Bloom's model from 7 billion to 506 million parameters. The key things to notice is the cost parity at the bottom. Yeah, this shows how many times the model needs to be used before the total energy used for inference equals to energy used for training. For example, for the largest model, the 7B, it takes around 590 million inferences. For the smallest ones, it's about the 200 million. That may shoot like a lot, but remember the ChatGPT gets about 10 million users per day. So that means for popular model, the total energy use for inference can quickly match up to the training, maybe in just a few weeks or months. So the inference may look cheaper at first, but it's add up fast. So that is why it's just as important to optimize the inference if we want to build a truly sustainable AI model. And we talk about the inference, but now let's ask, does the task itself matter? Yeah, the task will have different AI tasks and using very different amount of energy. Even when running on the same type of the hardware. So this chart shows the average energy used for 10 common machine learning tasks. All these will test using the same GPU and setup to make a fair comparison. Well, the main things to notice here is like the classification task, like text or image classification use the least energy, just a few thousands of kilowatt hour. And the generative tasks like summarize or generating text use about 10 times more energy than the classification. And the image generation is by far the most using the most energy. Most intensive task is using nearly 3 kilowatt hour per inference on average. So the one reason for this is the amount of output generated. For example, mask the language modeling only predict one token, but text generation might create a whole sentence, which takes much more processing. So when we think about the sustainable AI, it's not just about the model, it's also about what the model is doing. Yeah, we need to select the most suitable text. And you can see this chart, we can see a much bigger picture that's really drives emission during the inference. Like each dot here shows a different model based on how big it is, like the number of the parameters along the bottom and how much carbon it emits per inference on the left. And this is a clear pattern as model gets better, bigger, the emission usually go up. But that is not the whole story. You can also see a lot of variation here, even between models of similar size, because the type of the task still make the biggest difference. Like to put it in perspective, the most efficient task generation model use as little energy as about 9% of the smartphone charge for 1,000 inference. And the least efficient image generation model use the same energy as 522 for the phone charges for the same numbers of the inference. That means each inference used about half a phone charge is just to generate one image. So yeah, yes, the model size matters, but the task you ask the model to do is matters even more. So if yeah, so as we talked previously, if we want to build sustainable system, we need to choose not only smaller models but also the right model for the right job. So to wrap up, let's take a look at the real world use cases, the full life cycle energy and the carbon footprint of a chatbot powered by the large language model. So this is based on a method called life cycle assessment. That means we consider everything from beginning to the end, from the first idea to the final disposal. So according to the international standards, every part of the process, including the design, the production, use, and the recycling, as both involves energy use and emissions. And everyone involved, from the tech companies to user, that plays a role. So this chart shows 8 main phases. It starts with the research and development to design and testing the chatbot. Then the hardware is manufactured, and this including the GPU and the servers. And the next is the global shipping and the logistics, moving the equipment toward to the data center. Yeah, and operating and maintaining this facility also take energy. Then we have massive data collection and the storage, often like storing in a big and energy intensive data center. And after that, we reach model training and fine tuning, which we know is energy heavy. So once we deployed the model, we have chatbot service. So every time someone use the chatbot, it runs the inference. And finally, when the hardware is no longer usable, there is a recycling and all the disposal, which also has the carbon cost. So sustainability isn't just about the training, it's about the whole ecosystem of the building and the running AI system. So this is kind of full picture thinking what we need to make the AI deployment truly sustainable. Yeah. So let's take a closer look at the phase 6, the training and fine-tuning the large language model. This phase is one of the most energy intensive part of the entire life cycle. The number here, yeah, you can see is massive. Yeah. So for example, training a small model with 200 million parameters creates about 300 tons of the carbon emission. That's like 125 flights between Beijing to New York. Yeah. Then training a GPT-3, which is much bigger, used over 1,000 megawatt hours of the electricity and create more than 515 tons of the carbon emission. And like you can see for the GPT-4, it's even higher more. It's it's about 7,000 megawatt hours of the electricity and 3,000 tons of the carbon emission. And these numbers don't even count all the testing, fine-tuning and updates that happened before and after the final model is trained. So as model gets better, this energy and emission will go faster. And this is why we need to focusing on the make the training process more efficient. And now we can move to the phase 7 when the chatbot is actually used by people online or offline. So this is the part we most familiar with using the tools like the ChatGPT on our phones and computer to make the query. So like we talked previously, every time someone asked a question and get a reply, that is called the inference, yeah. And it's use energy. You can see here each individual prompt doesn't use much energy, but when you have million or even billion of users, it's really add up. So this chart show the different usage scenario and how much the electricity they used every month. It's yeah, in several of these scenario, like the energy used just to run the ChatGPT is actually higher than the energy used to train it. So you can see in the worst case scenario, the energy use is over 23,000 megawatt hours in 1 month. And based on recent traffic, around 1.5 billion visitors per month, the annual energy use of the ChatGPT could be more than 7 terawatt hours, which is lots of, yeah. So this use case help us understand that the 8 phases of the chatbot's life cycle is not just isolated. They actually they are connected. So each arrow in the first chart, this chart you can see they are connected and influence each other. So like research and development affect how we build the hardware and how we manage the data and how efficient the training is. And the way we build and use the hardware impact almost every other phases you can see. And from the the logistic to operation and even the recycling. So when user interact with a chatbot, they create new data, and that data is stored and used to retrain the model later. So the usage phases also loop back into the training and the data management. And even the final phase, recycling and disposal, can reduce the need for new hardware and cut energy use in production and shipping. And you can also see the right side, we can see the 3 system level pathway to help make this entire process more sustainable. So the pathway 1 is about the transparency, like doing full life cycle assessment and reporting emission clearly. And the second is focusing on shared responsibility, not just the companies, but also the research and the developers need to take action. And the path 3 involves the government standards and the long-term planning, so that sustainable AI become the default. So these 3 together to remind us not just single team can fix this alone. It's take a lot of coordination and to build the sustainable AI. And how we can track the emissions for our AI models. You can see some tools that could help us. And one is the cold carbon is a lightweight tools you can run during training or inference. It will measure how much energy your hardware used, like the GPU, the CPU, and the RAM, and then multiples them by the carbon intensity of the electricity in your region. So it gives you a good estimate of your model emission in the real time. And the carbon tracks is a bit different. It helps you to forecast the energy uses like before the training. It's useful when planning the large experiments so you can estimate the impact before running the full models. And also for the machine learning carbon emission impact calculator is a web-based tools where you can enter basic information about your model, like training times, the hardware used, and the location, and to get a carbon estimate. That is quick and easy to try to calculate on the website. So this tool is helpful when you want to make your model more sustainable or even just be aware of the impact. And here is another helpful tool that's called the LLM carbon. So this is designed to give a complex and end-to-end estimate of the carbon footprint for large language model. So it takes into the count is first is the model architecture, like how many parameters it has and how complex the math is and how it's scaled. And next is this will also calculate the hardware setup, such as the efficiency of the GPUs and how data is processed, and also the data center configuration, like including the cooling system and energy efficiency. That makes the truth special is combines both the operational emission and the embodied emission to give the total carbon emission output of your large language model. Yeah. So, and if you want to use, if you want to have a deeper look, you can see the links and see the publication they might give. And the last tool is very practical one. Is called the AI energy score. That is like the AI energy start rating, and it works a lot like the energy labels we are seeing on the home applications. So it gives model a star rating based on how energy efficient they are during the inference. This help user, especially the developer, choose the best model for the task. So it's not just based on the accuracy, but also on the energy use. And you can see if you want to doing the text generation or the image classification is choose will let you compare different model and see which one is using less the GPU energy. This is a part of the Hugging Face open source tools. So it's great way to make smarter and greener choice when picking a model, especially when scaling across lots of users. So now we have looked at the problem and how to measure it. Let's talk about how we can actually make models more efficient. So here are three key technologies for optimize the large language model. One is the distillation, like training the smaller model to learn from a larger one, and the quantization is to reducing the precision of the model numbers to make it faster and lighter, and pruning is to removing the part of the model that aren't really neat. So each of the math can help cut down on the energy use and make models run faster and cheaper. So both during the training and the inference. So let's through them one by one. First is the distillation is the one of the most popular technology for building the smaller or more efficient model. So like you can start with a big model called the teacher model instead of training the smaller model directly from the data. The smaller student model learn from the teacher model's prediction. So the idea is the teacher already know how to solve the task. So the student just learn to copy this behavior. So this process is called the knowledge distillation. It helps the student model learn faster and better even with fewer parameters. So the result is a much smaller model that still performs well, and this faster and is well more energy efficient during the inference. And next is the quantization. And the goal is to make the model smaller and faster by reducing the precision of these numbers. Because normally the model using the 32-bit floating point numbers, and that is very precise. Yeah, but also takes more memory to calculate them. So with the quantization, we can reduce that to 16-bit or even 8-bit values. It helps shrink the model size and make it run faster, especially on the low power hardware like phones or edge device. So these charts show how we keeping the same range of the values, but just using the fewer bits to represent them. So it can be done after the training. So that is why it's called the post-training quantization. So it does requires a bit of calibration to make sure the model still works well, but it's in many cases it's very little impact on the accuracy and a big impact of the efficient. And the third is to pruning. And the idea is very straightforward. We remove part of the model that aren't contributing much to this performance. Thinking like to trimming a tree, that you keep the strong branches and cut away the one that don't help its grow. So in neural network, pruning usually means to cutting out the neurons, the connection or even layers that don't activate much during the training. Yeah, so the model will become the smaller and uses less energy in the inferences. So there are different way to pruning. Something simple like removing small weight, and others are more complex. But in most cases, pruning helps you get the similar result with less computation. So that is great to make the large models more efficient without starting over from the scratch. And here is another more way we can reduce the energy use, especially during the fine tune of the large language model. So instead of updating all the weight in a model, that will also take lots of memory and power. We can use more efficient methods that like the LoRa and the QLoRa. And you can see it in the images on the left. With the full fine tune, the entire model is updated, and this is use a lot of 32-bit memory and require the powerful GPUs. And then in the middle is the LoRa, or like with is the low rank adaptation. Instead of charging the whole model, it's add a few small adapter layer that's trended separately. This will save memory. Is to will trend each layer separately. So this can speed the things up. And in the right is QLoRa. It goes a step further by using.
Sorry, Yilin, I tried to make a poll just for the fun of it. Sorry if it interrupted you. We still see your screen.
Okay, because it's
Sorry.
just the
Sorry.
pop-up.
I wanted to do it and see you not to, not to disturb you, but I guess it's not the case. Sorry.
Yeah.
Please go ahead.
Yeah, it's okay. I just continue, and you can continue the polling. Yeah. And yeah, let's see the QLoRa goes a step further by using the 4-bit model, which is even smaller and runs some part on the CPU instead of the GPU. Is very efficient to like for the limited hardware. So so these methods are especially useful if you want to fine-tune the large models on a smaller budget, or just reduce the energy impact of your work. And the best part is they often give the similar performance to the full fine-tuning. Yeah, So let's think about how to choose the right optimization method. Depends on your use case. So there are two main questions to ask. First is, does the method need to know more context? And the second is, does the model need to behave differently? So if you want to improve what the model knows, you can use the prompt engineering for the small tricks, or the RAG, the retrieval augmented generation, like to bring in the outside knowledge database. And if you want to improve how the model act, you might use the fine tuning or advanced method like LoRa. And of course, you can combine them both to get better result without always needing a bigger model. So this is kind of smart optimization, helps you to improve the performance, reduce the energy use, and choose the most efficient path for your problem. Yeah. And so far we have, I'll just look another quiz. Let's continue. Okay.
Sorry, let's continue. I'm still trying to learn about this post and I thought I closed it. Sorry.
Should I share in this? You can have a look.
No, no worries, no worries. We
Okay.
can discuss that later. Sorry. Please continue your course.
Have you personally used? No yet. Yeah. Yeah, because the and to training the larger model needs like to if you want to train it from scratch, that needs a lot of energy. So this like the quantization we talked about, the to optimize the model, that is very helpful to make your model smaller. Yeah, this is nice. Yeah. And here, yeah, we looked at the way to make method more efficient, but the real impact also comes from the infrastructure where and how models are run. Like first, we can choose energy efficient data center, especially those powered by the renewable energy. That make huge difference in reducing the emission. Like and also a good designer to the cooling system and power management. That's all important for the data centers. And for the hardware, it's including the using the newer and more efficient GPU, but also specialized chips and accelerators built just for AI that will be helped the efficient much better. And one is the most interesting one is we can use the AI at the edge. That's we can running the AI model on the local device like the phones, like the sensor or embedded system. So this avoid sending data back and forth to the cloud, which also save the energy, reducing the latency and improve the privacy. So both the location and hardware we use can help us build the faster and the greener and the smarter AI system. Yeah. And now let's go to the hands-on lab. We can put everything we have learned, we have talked about today into the practice. Can the lab link I already show you in the email and also in the community. And I will show you here also. Hope you already get the link. Yeah. Yeah, and you can see this depth is like we would like to measuring and optimize the carbon footprint of the large models is to learn how to measure and reduce the environmental impact of the small language model, because we just using the example to measure the energy tracking and the optimization technology. Yeah, and here we will run the inference with different transformer models, the bird and this tier bird and tiny bird and and we will to quantize the tiny bird. And we will track and compare the carbon emission and the energy consumption of this model and compare them and also to measure the accuracy using the task and reflect on how to make the AI choice that are both smart and sustainable. So here the first is to make sure you have all the necessary tools installed. We will be working with the Hugging Face models that can easily download and run. So like tracking carbon emission and testing the optimized inference. So we need a few specific library here. I already run it, yeah. And first is the transformer. This is the Hugging Face library that's give us access to powerful models like the birds and this tier bird. Yeah, and the torch is the deep learning back end for the most Hugging Face models. This can handle the compute. Yeah, and also we are using the cold carbon as I interested in the slides that can the tools we using the tracking the energy consumption and the carbon emission. Yeah, and here we will first to track the emission for the baseline model, the bird. So the original bird-based model is like the widely used transformer for the NLP. So we will using the cold carbon to track how much energy with the in the inference consumption. So and also using this to estimate the carbon footprint. And like we can analyze the like here is first to start the emission tracking for the bird. Is like here is the name of the project. We named this the bird-based in inference, and using this bird that is specific this is fine-tuned by the SST2 datasets, the bird of the model, and to do the sentiment analyze. And we using the one sentence inference to test that. And you can see the output, it can automatically automatically tracking the GPU and the CPU because we are run it in the collab. So if you run it in your locally, this will calculate your GPU, but here in the cloud we don't have the CPU. Yeah. So here we can see the energy that that compute is like here, and also like to do the prediction, the label. Yeah, the label is like the like the sentiment analyze label is like will output the label 1 or label 2. That means the positive negative, and the score is the accuracy of the model. Yeah, here that will track the energy consumption. And the next is to measure more compressed version of the bird. Is the this teal bird is a smaller and faster, cheaper version of the bird, like training using a technology called the, like we talked the destination. Yeah, it's learned to mimic the bird's output on a large data set, and it remains the 96% of the bird's understanding ability, but this will be 40% smaller and around 16% faster. Yeah, so that is make a great candidate for greener inference, especially when deploying in the edge, in the on device, on the edge device. So here is the same method to start the emission tracker and load the model and run the same inference, because we need to compare them. And the bird is also from the Hugging Face that's already fine-tuned. And yeah, here. So after we start the emission tracker, this will automatically like result in a field that's called the emission CSV, and that's this file will be like have the project name that we already have, and the duration, how long the text took, and the energy consumed, the in like kilowatt hours. Yeah, and the also the estimate the carbon emission. And here we can load the file to compare them. And yeah, next we will like to using the much more further compression model. The tiny bird is very compact version of the bird designed for the more lightweight deployment. So the tiny bird is trained using the task specific knowledge destination, means it's learned bird, but not just generate. It's specific for the task, like the sentiment classification. And it's even smaller than the distil birds, with as few as 4 transformer layer. And it often offer real-time inference of potential on mobile on edge devices. So here is the same one. And you can see, yeah, so the tiny bird is like, is perfectly for the low power environments like the mobile app and the embedded system or suitable where speed and energy saving matter the most because these have much lower energy cost. Yeah. And next so far we have reduced the emission by choosing a smaller models like the distant bird and the tiny bird. Now we'll try something different. We will using the optimizing how the model runs, not just how big it. So that's called the quantization. So like we introduced the quantization is by reducing the precision of the number used in the model, like from the standard 32-bit float to 8-bit float inters. So this will be less memory and faster computation and lower energy use. So if we want to using the quantization for the tiny bird, we need to exporting the Hugging Face, the tiny bird model into the ONNX format. It makes it the model more compatible with the ONNX runtime. So this is a high performance inference engine. Sorry. Yeah. And then we now we quantize the model by reducing this weight precision to 8-bit inter using the ONNX runtimes to do the quantization. So this step is what saves energy and speeds up the inference, especially using when running the model on CPU. Yeah. And next you can is using the emission tracker to calculate the energy emission, and now here is the result. Yeah. So here is the result, and then we can compare the emission for the pair project. As you see, the quantized tiny birds that we are using over 100 times less than even the tiny birds on this one. So that will clearly show how the different optimization methods to make the model more smaller and more less energy use. Yeah, and here not only for the energy use, we need to think about the accuracy. That's 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 how well the each model will perform. So to make sure that we will test each model in a real world test for the sentiment, also the sentiment classification, and using the same dataset, the SS2 datasets to test it. You can run it, yeah. And you can see here, because we first run the Hugging Face model species, easier to test it. Yeah. So you can see the bird-based has highest accuracy. This is large, powerful, and trended for the general LLP. Yeah. So the steel bird is keeps almost all the bird accuracy while using much less energy. And the tiny bird is will be faster, but is still lost much the accuracy about 12 percentage of the less than the bird. So this is an important trend off. So if you need the maximum accuracy, you might choose the bird. But you are care about the efficiency of the scale, like tiny bird might be worth to modify it. And also, we already using the quantization reduce emission mostly. Now let's see how to test the accuracy of our the quantized ONX tiny bird model. Also in the same SST2 sentiment data set. Yeah, you can run this part and you can see the accuracy will be much lower. Yeah, but don't be scared because let's compare them, because it's not only for the accuracy. We need to compare the energy consumption also. Let's see here. Yeah, you can see the see the everything we measured in here. So this is chart show the accuracy on the x and is how well is performed the task, and the carbon emission on the y is the energy during the inference. So definitely the bird-based is the most accurate, but also the most carbon-intensive model per inference. And this tier birds gives us nearly the same performance with significant lower emission. And the tiny birds, like these will scarify some accuracy, but offer the with real saving of the energy. So that is ideally for the age, and also the quantize the tiny bird, the ONX shows that possible that's with the precision optimization. Yeah, so that's will still that's accuracy is around 79% percentage is still very good. So if you ask what's the best trade-off, that's must be the distill bird that's reminds almost all the accuracy of the bird, only 0.005 lower. So but that's much less the carbon emission than the bird, and has much shorter inference times, as you can see. You see here the time I didn't show up, but here you can see the duration. Yeah, that is the lab. I want to show you the different methods to optimize the AI model will perform. Yeah, and you can also run the task on your locally or you can change the different AI model to test how much this will be lost and how to choose the best model to for your training. Yeah. Yeah. So to quick wrap up, here's what we talk about today is first, why sustainable AI matter, because the training and using the large models create real energy and the carbon cost, and like what the emission, the embodied emission and operational emission, that's both contribute to the total footprint, and how the task, the model size, and the infrastructure all affect the energy use. And like I also introduced the tools like carbon, cold carbon, like here I used, and lots of tools can help us to measure the impact. Yeah. And here is like to show how the optimization method, the distillation, the pruning, and the quantization will to affect the infrastructure, affect the AI model.